Charging and discharging graphs for capacitors. As time increases, the current decreases. That's because, as we saw in the previous PowerPoint, when the capacitor is charging, we have initial large flow of electrons towards the plates. However, as the plate builds up negative charge, it becomes more and more repulsive to further electrons going onto it. So the charge flow onto the plate of the capacitor very, very quickly at the start and then very slowly afterwards. Charge is not flowing constantly, and charge cannot flow across the gap between the plates. So we have here a graph showing current with an initial high rate decreasing over time to the point where it reaches zero. The current flowing in the circuit depends on the voltage of the supply and the resistance within the circuit only. So irrespective of what the capacitor value is, it is only determined by the value of the supply voltage and resistance. The maximum current, the current at switch on, Imax, is determined by the relationship Imax is equal to voltage supply divided by resistor. We say that the capacitor is fully charged when the potential difference across the plates is equal to the EMF of the battery and the current no longer flows in the circuit. Notice not through the capacitor, because current doesn't flow through a capacitor. It's got an insulator in the middle. We talk about the current in the circuit. So the initial charging current, the maximum current, is equal to the EMF of the supply divided by the load resistance. Now this is not in the data booklet, it's not in a relationship sheet, so it's not in a square, but it's very, very useful to note because it's a common question. So we put that into a circle. Increasing the resistance in the charge-discharge circuit causes a lower charge or discharge current. So the larger the resistance, the smaller the current. If I've got a small current, that means it's going to take longer for the capacitor to charge or discharge to a certain voltage. We can vary the resistance and the capacitance within the circuit, and that will affect the current discharge graph, current charge graph. So changing the value of the resistor, we see that we have, for a large resistance, a smaller starting current and a longer time for the capacitor to charge. If we decrease the size of the resistance, we have a higher initial charging current and a smaller time for the capacitor to charge. The area underneath the current time graph is equal to the charge stored. And if you looked at those two areas, they are equal to each other. It would be very hard to calculate it from that shape of the graph. So increasing the value of the resistance decreases the initial charging current and increases the time for the capacitor to charge, as there's less charge getting to the plate per second. If we vary the value of the capacitor, we can see there's no effect whatsoever on the value of the initial charging current. And that's because the initial charging current is only determined by the value of the resistance. However, a large capacitor requires more charge to be stored per unit volt. So if I've got one large capacitor with a 10 volt supply and a small capacitor with a 10 volt supply, the capacitor with the higher value is going to take longer to charge because it needs more charge to reach that 10 volts. So we can see from the graph that increasing the value of the capacitance will not affect the initial charging current. However, it will increase the time for the capacitor to charge. A smaller value capacitor, again, will have no effect whatsoever on the charging current, but will take less time to charge. If we look at the discharging graphs, we see a very similar pattern. A high initial charging current determined by the resistance in the circuit, gradually reducing over time to zero. However, we can see that the current is now flowing in the opposite direction. Whereas before, electrons are flowing to the negative plate, what became the negative plate, now they're flowing away from the negative plate because they want to get towards the positive. As time increases, the current decreases, or we can say it goes towards zero, and this means that charge flows onto, that is, off the plates of the capacitor quickly at the start and very slowly later on. Charge is not flowing across the gap between the plates. The current is negative because electrons flow off the capacitor in the opposite direction. So in summary, the initial charging current, I max, is equal to the EMF of the supply divided by the resistance. Current starts at a maximum and gradually reduces to zero. If the value of the resistance is increased, the initial discharging current goes down. The time taken to discharge and discharge will increase. The area underneath the IT graph is the same each time. If the value of the capacitor is increased, the initial charging current will be the same. The capacitor takes longer to charge to the same potential difference as more charge is required to do so, and the area underneath the IT graph will be greater as the charge stored will be greater. Now, we can investigate further the charging characteristics by looking at the voltage. The circuit below can be used to investigate the voltage, charge, and discharge characteristic for a capacitor when we connect it in series with a resistor. So the capacitor in the circuit will charge when the switch is at position B. That is, it's connected in series with the supply. If we move the switch to position A, then it's going to discharge through the wire. From this, we get the following graphs. We can see, whilst we're charging, that the voltage starts at zero when the capacitor is initially uncharged and gradually increases up to the value of the supply EMF. Now, we can see that the rate of charge is greatest at the start, and that's because that's when the current value is at its largest amount. So as we're charging, the voltage increases towards the supply across the capacitor, but because this is a series circuit and the voltage supply is split in between the capacitor and the resistor, if the voltage across the capacitor increases, the voltage across the resistor must have gone down. So at the initial point before we're charging, all of the potential is across the resistor, none of it is across the capacitor. When the capacitor is fully charged, all of the potential is across the capacitor and none of it is across the resistor. The maximum potential across the capacitor is equal to the EMF. When the capacitor has a voltage value is equal to the EMF, the voltage across the resistor is equal to zero because the current is equal to zero also. The charging current at any particular time can be found by using I is equal to the voltage across the resistance divided by the value of the resistance. So we know that the current changes with time. We can determine the current at any time by using good old-fashioned Ohm's law. That relationship, how the sum of the voltage across the capacitor and the sum of the voltage across the resistor is equal to the EMF, is really, really useful. Again, it's not on the relationship sheet, but it's a useful relationship, so that's why we put it into a circle. If we look at the discharge graph for voltage, as the cell is no longer part of the circuit because we've moved to the second position, position A, the capacitor now acts as a source of voltage, like a cell itself. It's providing a potential to the resistance. So the voltage across the capacitance is equal to the voltage across the resistance in magnitude. The charging current at a particular time can be found by using the relationship of voltage across the resistance and the current and the resistance of the resistance. We can see that the voltage across the capacitance decreases over time towards zero, as does the value of the resistance, but they are flowing in opposite directions because electrons now flow through R in the opposite direction from the capacitor. The voltage across R must have changed direction. In order to find the value of the current, as I said, we can use VR over R to good old-fashioned Ohm's law, but because the value of the voltage across the resistor is the same as the value of the voltage across the capacitor, we could use either of those in order to determine the current at any one particular point. Again, just as we saw, varying values of the resistance and the capacitance will affect the current and will also affect the voltage. So we can see that if we have a small value of R, then we're going to have a smaller time for the voltage to reach the same as the supply. when it's charging, or the voltage to reach the same as the supply when it's discharging. Here, if we're looking at the graphs across the voltage across the resistor, we can see the differences in the charge time due to a large value of R or a small value of R. Varying this in terms of the voltage, we can see that small values of capacitance and large values of capacitance again will have exactly the same effect as we saw with the current. That is, a large capacitor is going to take longer to charge than a small capacitor. A small value of capacitance won't affect the overall final value of the voltage. However, it just means you'll take longer to get there. When a capacitor is fully charged, remember the voltage across the capacitor is equal to the EMF. So in summary, increasing resistance or capacitance increases the time for the capacitor to charge or to discharge. Increasing the value of resistance also decreases the magnitude of the initial charging current. Increasing the capacitance also increases the maximum energy stored. And note that the maximum energy stored can also be increased by increasing the supply voltage, as E is equal to 1/2 CV squared. Again, a very common SQA question.